Okay, let's go ahead and look at the synthesis of aspirin. Okay, so in this reaction, what we have done is we have added an acid along with an alcohol. We'll just name this ROH. And we have an acid anhydride, specifically acetic anhydride. We'll call this R prime. And this is a generic acid anhydride, and this is double prime. Now for acetic anhydride, the R prime and the R double prime are the same thing, which is just a carbon and 3 hydrogens on the end there. Let's look at this reaction in a general sense. And the first step is going to be activation of the carbonyl group. Okay, so we have our alcohol here, and this is just going to be sitting in the background for just a minute. And we have our acid with the acidic hydrogen. And then we have our acid anhydride. So what's going to happen is that a lone pair on one of the oxygens on the carbonyl, the double bond to the carbon, is going to go ahead and form a bond with the hydrogen on an acid. Now, it doesn't really matter which one of these oxygens we choose. It could be this one right here, or it could be this one right here. And in reality, they'll both happen. Now, if R prime and R double prime are the same thing, which is what we would typically want to use in a chemical reaction. That way, no matter which one of these oxygens becomes protonated, we'll get the product we're looking for. But in this scenario, because that oxygen is formed a bond with the hydrogen, what is going to happen is that the bond here is going to break, and those electrons are going to move onto the conjugate base. And so what we would get is this right here. Our R prime R double prime, and we have this oxygen that has a positive charge on it now. Now, if we think about resonance structure, it doesn't make sense that the oxygen is going to have a positive charge. We could actually have this move on to the oxygen, so the pi bond is going to move on, become a lone pair, and what we would get is this right here. And now the positive charge is on the carbon. The carbon only has 3 bonds in this scenario. And so this is called activation of the carbonyl group. And what this results in is this carbon becoming positively charged, which is going to attract a nucleophile. Now in this scenario, the alcohol, the ROH, is going to act as that nucleophile. And so in the second step, what we're going to have here is going to be an attack on the electrophile by the nucleophile. So we have our alcohol, and the lone pair on this oxygen is going to come up and is going to form a bond with that carbon. And so the resulting structure is going to look like this. We have our R prime, our double prime, and now we have a lone pair on the oxygen. It's also bonded to hydrogen and our R group. And this oxygen now has the positive charge on it. So now what we have is our conjugate base is going to come over here, and conjugate base is going to remove the hydrogen, and the electrons that were in that bond are going to jump onto that oxygen here. So what we will get R prime, got my lone pairs over here, going to our double prime. And now we have oxygen right here. And we have our R group that was on the alcohol hanging off. And we have our acid with the proton. Okay, so now what we have is something called a leaving group. And so a leaving group is often denoted Lg, is an atom or a group of atoms that becomes detached from the main molecule. So what I'm going to do is I'm going to highlight this right here. So this right here is going to become our leaving group. This thing is going to detach from the rest of the molecule. And so I can see that here. So how does this occur? So what happens is one of these lone pair of electrons is going to, wrong pen. One of these lone pairs of electrons right here is going to move down and make a double bond. Now, that can't be allowed for the carbon. The carbon is on the second period. It is not allowed to break that octet. And so what's going to happen is that one of these other bonds has to break. And so what we have is this oxygen right here has two lone pairs. This bond right here is going to break, and it's going to jump on to this oxygen. So now we have our R prime. Connected with our R. And, oh, you know what? This right here is a hydrogen that has a plus. And then we have oxygen going to the R, plus this group right here. This is our leaving group. R double prime. Now the reason why this makes a good leaving group is because through resonance, what we can actually see, these two things are resonance structures of each other, is that this lone pair can form a double bond, and then we can distribute the charge. So now we have negative was over here, and now we have our negative charge right here. So that stability, that ability to distribute the electric charge, or that negative charge, throughout the structure makes that structure stable and therefore a good leaving group. Okay, so the next step is what we have here. We have our R prime, goes to the oxygen, the hydrogen, and then we have our leaving group that's floating around here. This leaving group has an oxygen that has a negative charge on it. And so one of these lone pairs comes over here, forms a bond with the hydrogen, and that jumps onto the oxygen. And what we are left with is this structure right here, along with our leaving group, which has become protonated. Okay, so that is the generic reaction for an alcohol reacting with an acid anhydride. And what we are going to be left with is going to be these molecules right here. So let's go ahead and look at this in a more specific circumstance, such as the reaction of salicylic acid with the acid anhydride. So again, in this reaction, our acid is going to be sulfuric acid, and then we have acetic anhydride. And so what this is this molecule here. And so in this case, R prime and R double prime are the same thing. And an acid anhydride is when you have a carbonyl group, which is a carbon double bonded to an oxygen, and then that's bonded to an oxygen, which is bonded to another carbon that is in a carbonyl group with an oxygen. And then these groups over here have to be some other carbon or chain of carbons or something of that nature. Okay, so we also have salicylic acid. This real quick in its skeletal structure. looks like this. Salicylic acid is going to be a benzene ring or an aromatic ring. And it has a carboxylic acid here, and then it has an alcohol here. And this molecule, I can draw this another way, is equal to this right here. I'm just flipping how I show the connection between the carboxylic acid and the alcohol. So alcohol on top on the right, alcohol on bottom on the left, carboxylic acid on the top on the left and on the bottom on the right. Okay, so for this group, what I'm going to show you is I'm just going to go ahead and say that this is equal to R. And so what that means is that ROH, as we saw before, is equal to this right here. And we can see that each of these methyl groups on the end is going to be the R prime and the R double prime. In this case, R prime and R double prime are the same. So I'm going to color code these molecules and we'll go ahead and show them in action. I am not going to write out the H2SO4 every single time. I'll just write HA. So I'll have my acid here. I'll do my acetic anhydride. Right here. So in the first step, we have activation of the carbonyl group. Now we of course know that that activates the carbon. I can show the resonance structure. So that jumps up onto here. So that is the same thing. We have a positive charge on the oxygen in that one. And now, positive charge on the carbon on this one. Okay, this is where our nucleophile is going to come in. Nucleophile is the electron-rich oxygen on the salicylic acid and the alcohol part specifically. And so one of those is going to come in, is going to form a bond there. And so what we get in our next step is going to be this right here. This right here. Okay, so we have our conjugate base that was left over from our acid. Acid is right here. And so the electrons, lone pair on the acid, are going to form a bond with that hydrogen. This bond is going to jump on to the oxygen. And then we'll get this molecule down here along with our acid, which has been reformed. Okay, and this is where we have our leaving group. So I'm going to highlight our leaving group again here. So our leaving group is right there. Something I didn't carry down with me here was this lone pair of electrons on that oxygen. Okay, so one of these lone pairs right here is going to come down here and it's going to form a double bond. And when it does that, this bond right here is going to break and those electrons are going to get kicked off onto that oxygen. And so what we have is this molecule. Right here, which is almost aspirin. We of course have our leaving group, which now has a negative charge on it, but one of those is going to come over here and grab that hydrogen, and that bond right there is going to jump onto the oxygen. And what we are left over with is acetic acid right here and our aspirin. Okay, and when we're looking at this, what I should point out is that this whole group right here, well, that's that part right there in case you didn't see it. And then I'll just go ahead and point this out. This green part is this right here. And then we have our leaving group over here that has become protonated with the hydrogen, which was right here. And what we're left with acetic acid and aspirin.